Welcome to Lab 4 of our Signal Integrity Basics series. In this lab, we confront a persistent challenge in high-speed digital design, crosstalk. This phenomenon occurs when unwanted energy from one signal impacts a neighboring signal, potentially compromising system performance. Our objectives for this lab are to visualize and interpret electromagnetic interference plots within a simulation environment, and to understand the mechanisms and implications of coupling between transmission lines. In modern PCB design, usually with dense routing and fast switching signals, traces are not isolated. They interact through mutual capacitance and inductance with adjacent metal structures, including other signals, power planes, and ground planes. This interaction leads to crosstalk, where the electromagnetic field of an aggressor signal induces noise into a victim signal. Suppose you are designing a bus and you want to guarantee that no more than 150 millivolts of crosstalk can occur on any of the signals. A typical single-ended bus in a modern system may contain many nets in parallel, often 16, 32, or even more signals. However, when you simulate for crosstalk, you would not bother simulating all lines on the bus simultaneously. Instead, you would take advantage of the fact that crosstalk driven into a given victim trace comes predominantly from the two adjacent traces on the same layer. Begin by invoking Siemens HyperLynx SI. Navigate to your SI Basics lab directory via Windows File Explorer. Then double-click on the Launch HyperLynx SI icon. Next, we will open the schematic file pertinent to this exercise. Select Browse, Line Sim Projects, Open Schematic, then locate the directory HL Workshops and navigate to the Crosstalk Labs folder. From here, you'll open the file crosstalk.ffs. For crosstalk to occur, traces must be electromagnetically coupled. We will now explicitly couple TL1 and TL2 within HyperLynx. Click and drag to select both TL1 and TL2 on the schematic. They will be highlighted in red. Then right-click on TL1 and select Couple. This action invokes the Edit Transmission Line window, which now displays properties for a coupled pair. This window is central to defining and modifying the physical relationships between our traces. Navigate to the Create Edit Coupling Regions tab. Here, you can observe and modify key physical parameters like the length of coupled lines, their individual trace widths, the specific PCB layer they will route on, and their separation distance. The impedance window dynamically displays the characteristic impedance for each individual line, as well as the differential impedance for the pair. We won't delve into differential impedance in this lab, so let's continue to the Field Solver tab. Click Start to initiate the electromagnetic, or EM, simulation. Observe the visual representation of electromagnetic fields. Red lines denote magnetic field lines, and blue lines represent electric field lines. Pay attention to how these fields interact between the two traces. The extent of field overlap visually indicates the degree of coupling. While propagation modes are a topic for another lesson, this visualization provides an intuitive understanding of the energy transfer between two traces. Once you have reviewed the fields, close the Edit Transmission Line window. Coupled energy propagates backward and forward on a victim transmission line and arrives at the near and far ends as near-end crosstalk, or NEXT, and far-end crosstalk, FEXT. The FEXT and NEXT waveforms have different profiles. NEXT increases to a fixed level in the time relative to the aggressor's rise and fall time, and then remains at that level for a time twice that of the transmission line delay. FEXT increases in voltage with longer coupling length and arrives at the far end at the same time the aggressor signal arrives at the far end. Its time duration is the same as the aggressor's rise and fall time. It is necessary to assign a victim and aggressor's net in order to simulate crosstalk because they let us model how real PCB geometries would allow electrical and magnetic fields to spread beyond a single trace. As the aggressor toggles, It changes voltage and current interacts with capacitive and inductive coupling paths that distort the victim's waveform, introduce unwanted noise, or even shift its timing. Understanding aggressor and victim's interactions helps evaluate spacing, layer usage, driver rise and fall times, and routing topologies to ensure that high-speed channels meet their noise and timing margins. To simulate crosstalk, we must designate an aggressor net, the source of the unwanted energy, and a victim net, the line experiencing the noise. Double-click on U3.1 on the schematic to open the Assign Models window. Set U3.1 to a buffer setting of Stuck Low. This configuration ensures that this pin remains quiescent, making it our victim net, while the other active trace will act as our aggressor. Our first experiment investigates how the coupled length influences crosstalk. We will use the Sweeps with Oscilloscope feature. Select Signal Integrity, Sweeps, Sweeps with Oscilloscope. In the Sweeps window, expand Coupling Regions and then Coupling 0001. Double-click on the length line item to configure the sweep parameters. Set the initial length to 0.5 inches, the final length to 5 inches, and the simulation count to 3. This will run 3 simulations with different coupled lengths within this range. Click OK, and now click Run Sweeps. This action will invoke the digital oscilloscope. Set the vertical scale to 500 millivolts per division and the horizontal scale to 1 nanosecond per division. Then click Start Sweeps. Once the sweeps are complete, let's analyze the results. Uncheck the probes for U1.1 and U2.1 to solely focus on the victim nets, and click Zoom Fit to properly view the victim net's waveform. Observe the waveform for NEXT shown by the U3 probe and FEXT shown by the U4 probe. You should notice that as the coupled length increases, both NEXT and FEXT generally increase. Importantly, for this specific configuration, you might observe that the FEXT exceeds the NEXT. This is a critical observation. If your design had a crosstalk constraint, for example, a maximum of 80 millivolts, this FEXT could cause a design failure. This design clearly demonstrates that longer coupled lengths lead to increased crosstalk, as there are more physical proximity over which the electromagnetic fields can interact. Now minimize the digital oscilloscope and head back to LineSim. Next, we will investigate the effect of trace separation. Back in the LineSim window, select Signal Integrity, Sweeps, Sweeps with Oscilloscope again, this time unchecking the box next to Length to disable the Length sweep. Instead, double-click on the Separation line item to configure its sweep. Set the initial separation to 10 mils, final separation to 50 mils, and the simulation count to 3. Click OK, then click Run Sweeps. This will again invoke the digital oscilloscope. Click Start Sweeps. Observe the effects of trace separation on the NEXT and FEXT waveforms. You should see that as the separation between traces increases, the magnitude of both the near-end and far-end crosstalks significantly decreases. This is because increasing the distance between traces weakens the capacitive and inductive coupling between them. This directly relates to a common PCB design guideline, the 3x rule. This rule suggests that 2 parallel PCB traces should be spaced at least 3 times their space width apart to minimize crosstalk. While not eliminating crosstalk entirely, this spacing typically reduces coupling sufficiently for most digital signals to meet their margins at typical speeds. For very dense routing, however, this rule may not always be practical, necessitating other mitigation strategies. Let's minimize the digital oscilloscope and return to the LineSim window. Visually confirm the impact of the 3x rule on electromagnetic fields. Double-click on TL1 to open the Edit Transmission Line window. Note that the trace width is 6 mils and the trace-to-trace separation is currently 8 mils. This configuration does not adhere to the 3x rule. Go to the Field Solver tab and click Start. Observe the EM fields. You should see a noticeable number of connecting electrical field lines and magnetic field lines that appear close to interfering with one another, indicating significant coupling. Now, return to the Create Edit Coupling Regions tab. Change the trace-to-trace separation to 18 mils, which is 3 times the trace width. Go back to the Field Solver tab and click Start. You should now observe a dramatic reduction in connecting electrical field lines and magnetic field lines. This visual change clearly demonstrates how increased separation effectively reduces the electromagnetic coupling between traces. We have so far focused on microstrip-like configurations. Now, let's briefly examine these effects on a strip-line trace. Strip lines are traces embedded within the PCB stackup, sandwiched between a ground plane or power plane, offering better shielding and often lower crosstalk compared to microstrips. In LineSim, double-click TL1 to invoke the Edit Transmission Line window. With TL1 selected in the coupling regions, change its layer to 3 signal inner layer 1. Do the same for TL2. Observe how the transmission line moves down in the stackup visualizer, now being fully enclosed by the dielectric. Set the trace width of both TL1 and TL2 to 6 mils. Now, let's review the EMI. Set the trace-to-trace separation to 8 mils. Go to the Field Solver tab and click Start. Notice how the magnetic field lines of each trace are still interfering, even in a strip line configuration, due to insufficient separation. Return to the Create Edit Coupling Regions tab and change the trace-to-trace separation to 18 mils, following the 3x trace width rule. Go to the Field Solver tab and click Start. You should now see a significant reduction or even absence of connecting magnetic field lines, indicating much lower coupling. This reinforces that even for strip lines, proper spacing is critical. To further confirm these observations, we will quickly run some sweeps for the strip line traces. First, sweep the trace length. Select Signal Integrity, Sweeps, Sweeps with Oscilloscope. Double-click Length and set the initial to 0.5 inch, final to 5 inch, and simulation count to 3. Click OK, then run sweeps. In the digital oscilloscope, click Start Sweeps. Observe the increasing in the near end and far end crosstalk with length, similar to microstrips. Next, sweep the trace separation. Back in LineSim, select the Signal Integrity Sweeps, Sweeps with Oscilloscope. Uncheck Length and double-click Separation. Set the initial to 10 mils, final to 50 mils, and simulation count to 3. Click OK, then run sweeps. In the digital oscilloscope, click Start Sweeps again. Then observe the decrease in near end and far end crosstalk with increased separation, again mirroring microstrip behavior, but often with a lower overall magnitude due to the inherent shielding of a strip line structure. To conclude this exercise, we have utilized HyperLynx SI to observe and quantify the effects of crosstalk, a critical signal integrity concern. We've seen how electromagnetic fields couple between adjacent traces and how this coupling leads to both near-end and far-end crosstalk. I encourage you to continue experimenting with different trace geometries, stack-up configurations, and signal characteristics within HyperLynx to deepen your understanding of crosstalk mitigation.